Okay, so the idea today is to do a question answer review session. Final is obviously Monday. You've got the big bonus assignment that is open on WebAssign. I've got a version of that pulled up. I may have like different numbers than you, but I have the same. So like your number 5 is going to be like my number 5, but maybe with different numbers. So I can do any problems from that, or we can do stuff from old exams or old review or any homework stuff. Um, I'll let you guys kind of lead it, and then you can either unmute yourself to ask questions or you can put them in chat. Yeah. So, okay. So, number 5, it sounds like I was just picking that at random. But yeah, let's start with number 5. You guys are asking to go over number 5 in chat. So, let's see what number 5 is. Okay. So, it says, I'll go ahead and just share this real quick so everybody can see the question. So the one that I've got says use the disk method or the shell method to find the volumes of the solids generated by revolving the region bounded by the graphs of the equations about the given line. So about these 4 lines. So I'm going to jot this down and then I'll share the screen in just a second. So number 5, we've got y equals square root of x, y equals 3, and x equals 0 about, and then part A is the x-axis, so we're revolving about the x-axis, then the y-axis, or I'm sorry, then the line y equals 3, then the y-axis, and then x equals -1. So let's kind of review this. So again, the directions, I didn't write those down. I wrote this stuff down on my iPad. I want to share it here in just a second. But it says use the disk method or the shell method to find the volumes of the solids generated by revolving the region bounded by the graphs of these equations about these given lines. So, okay, so let's look at that and kind of review what we're doing here. Okay, so we've got the region bounded by these 3 curves revolved about these. So when you're doing these problems, the first thing you want to do is get a good sketch of the region. So let's go ahead and do that. So y equals square root of x looks like this. So it starts at 0, 0 and kind of goes up like that. And then I think y equals 3 is different from one version of this to the other. But y equals 3 is going to be a horizontal line at 3. And so we're looking at a horizontal line up here, and there's some intersection point there. And then x equals 0 is the y-axis. So the region we're looking at is actually the region up here. So I'm going to erase the shading in just a second, but it's above the square root graph and underneath the line y equals 3 or y equals whatever you guys have. Does that make sense to everybody? That that's the region we want to deal with? Everybody clear how to pick that out? Okay, so then let's draw a rectangle. So we get that region, we draw a rectangle within the region. So we'll use different color. This rectangle could go up and down or left to right. We'll just kind of default to up and down when we're doing this, and then that makes the problem dx. So remember that when we were first talking about this, if it goes up and down, you want the top boundary to remain the same everywhere within the region. You want the bottom boundary to remain the same everywhere within the region, which it does here. So this is fine. If you went left to right, you wanted the left boundary to be the same and the right boundary to be the same, that would be okay too. So we could do this problem that way just as easily. We'll just stick with this since we've got it. And then dx means we want everything solved for y. So when you do dx, you need y as a function of x. When you do dy, you need x as a function of y. So we're going to write this as y equals the square root of x, which is what we were given for this curve over here. And actually, I might label it underneath because it's going to be the bottom curve if we're talking about the locations of these. So this is y equals square root of x. This is y equals 3 up here. And then the last thing we need to do with the region is we need to get this intersection point. So we know that y is 3 on that, and we know that it goes through y equals square root of x. So to get that intersection point, we're going to set 3 equal to the square root of x, which means that x is 9. So this is the point 9, 3. And then that should be all we need to get the region set up. Any questions on how to set that up? Feel free to unmute yourself and ask, or type something in chat if you have a question about it. Is everybody good? Okay, so then once we have that, now to revolve around these various lines, then we figure out which method we're going to use. And so let's kind of summarize the way that we did volume at the time. So we had, for volume, we discussed it pretty informally, which we're going to continue to do. So we had the dishwasher method, and we have the shell method. And the dishwasher method, oops, let's make that a little more legible. Oops. The dishwasher method is when we think of the rectangle as being perpendicular to the line we're revolving around, and we put that in quotes because that's very informal to say that, but we think of this rectangle as being vertical, even though that doesn't really exist, but we think of it as being vertical. And so if the rectangle is perpendicular to the line, we use the dishwasher method. If the rectangle is parallel to the line, when we think of it that way, we use the shell method. Yeah, so we will also do one with dy. In fact, why don't we just do this problem both ways? So somebody in chat's asking, can we do it with dy as well? And yeah, we'll just do both ways. Does that work? Or we can do another problem if you guys have one, but we can set this up both ways. So, okay, so the dishwasher method is the volume is pi times the integral of the big radius squared minus the small radius squared times the thickness of the rectangle, either dx or dy. And the shell method volume is 2 pi rh. So 2 pi integral rh, and then either dx or dy there. Here on the shell method, big R is the distance from the line to the farther end of the rectangle. And small r is the distance from the line that you're revolving around to the closer end of the rectangle. And then over here, small r is the distance from the rectangle to the line. They're parallel, so there's not two separate distances. So distance from the rectangle to the line, or from the line to the rectangle, same thing. And h is the height of the rectangle. Okay, so that's kind of a summary of the two main methods that we were using to calculate volume. And so if we go back up here, when we're talking about the x-axis, if we're going to use dx, which we'll do that in this light or blue color, and then I'll go through and do a dy example with the same region here in just a second. But if we're going to use dx, so then the rectangle is vertical and the x-axis is down here. So the rectangle we think of as being perpendicular to the x-axis. So we're going to use the dishwasher method. So we need a big R and a small r. And so big R is the distance from the farther end of the rectangle to the x-axis. Well, the farther end happens to be up here. So when we do vertical distances, you take the top y minus the bottom y. Within that distance, the top y is 3, the bottom y is 0. So big R is 3 minus 0, which is 3. So it's 3 the entire time in that region. The small radius, little r of x, is the distance from the closer end of the rectangle to that line. So the closer end is here, the line is here. So that's again top minus bottom. Top y is square root of x, bottom y is 0. So we get square root of x minus 0, which is square root of x. And then the volume there is pi big R squared minus little r squared. So pi times the integral 3 squared minus the square root of x squared dx. And now we want to add those for all of the rectangles in the region. Well, it's dx, so we want the smallest x to the biggest x. Well, the smallest x in the region on the left is 0. The biggest x of the region is on the right, and that's 9. And so we go from 0 to 9. And so this is the setup. I think this problem does want you to evaluate it, but does everybody follow it to there? Any questions? Pretty good. Okay. So then let's go ahead and evaluate this one. I probably won't evaluate every single one of them, but we can if they're ones that people have questions on. But to evaluate this, we would do pi integral 0 to 9 of 9 minus x dx, because 3 squared is 9, obviously, and then square root of x squared is just x. And then we now do the antiderivative of that. So we get pi times, and then the antiderivative is 9x minus 1/2 x squared from 0 to 9. So we get pi times, and now it's 9 times 9, so 81 minus 1/2 times 9 squared, so 1/2 times 81. And then it's 0 minus 0. You do want to double check that you actually get 0 there. And then 81 minus 81 halves is 81 halves. And so we get 81 pi over 2 if you simplify that. And that would be the answer. Does anybody have any questions on how to set up part A or evaluate that? Everybody good?
Only part is, how did you find the intercept of 9, 3?
9, 3. I set 3 equal to the square root of x. My bad, I erased that. But because we know that it's on the graph y equals square root of x, and it's also on the graph y equals 3.
Okay.
And then you solve that and get x equals 9. Does that make
All
sense?
right. Yep, makes sense.
No problem. Other questions, you guys? Everybody good? Okay, so then let's go. So that is part A. And now part B is y equals 3. So y equals 3 again is going to be the dishwasher method, but we're revolving up here. So we're going to have a big R and a small r. So big R is the distance from the farther end of the rectangle to this line. So remember, we're looking at this line to the farther end of the rectangle. Well, that's the top y, which is 3, minus the bottom y, which is the square root of x. And then when we talk about the small r, that's the distance from the closer end of the rectangle to the line. Well, the closer end of the rectangle is on the line. So top y minus bottom y is 3 minus 3, and so small r is actually 0. So the volume is pi times the integral from 0 to 9 of 3 minus the square root of x squared, and technically minus 0 squared, but that will fall out, dx. And then to get you started on evaluating that, you would go pi times the integral 0 to 9, and you would expand this, and you would get 9 minus 6 square root of x plus x dx. And I'm happy to continue that. So if you'd like to see that worked out, let me know in chat. But if we're comfortable with that, I'll skip so that we can get to more questions. Is everybody comfortable doing it from there? Okay. Anybody that wants me to say it, just type in chat real quick and I'm happy to work it. Okay, so we go from there and get an answer. Now for the y-axis, this time the rectangle is parallel to the line, so we're revolving around the y-axis. That's when we use the shell method. So we're going to go with 2 pi rh. And so the r function is the distance from the rectangle to the line. Remember, we're revolving around the y-axis. So this is a horizontal distance. You take the x here minus the x here. So right x minus left x. The right x is x. and the left x is 0. So we get a radius function of just x. The height h is the height of the rectangle. That in this case is top y minus bottom y. So we get 3 minus the square root of x. So volume is 2 pi integral of r times h. So x times 3 square root of x dx. Okay, question in chat is how did I get r? It's the distance from the rectangle to the line. So the distance from here to here. And I will get rid of this arrow. So the distance from the rectangle to the line, it's a horizontal distance. So you take the x on the right, which is just x, and the x on the left, which is 0. Does that make sense? So x minus 0, which is then x. Okay, cool. Other questions, you guys? All right. And then we want to add this again from 0 to 9. Whoops, got it on erase. My bad. So 0 to 9, because we want all the x's in the region. So then to simplify this, I would pull the 3 out, and so we get 6 pi integral 0 to 9, and then x times the square root of x is x to the 3 halves, because it's x to the 1 times x to the 1/2. And now again, I'm happy to work this if you'd like to see it, but you would do the power rule and plug in 9, plug in 0, and subtract. Is everybody comfortable from there?
Is that 3 root x or 3 minus root x?
I'm sorry, where? Here? Oh man, my fault. It is for sure 3 minus root x, my fault. So let's fix that. Man, it's for sure 3 minus root x right here. My bad, guys. So it's okay, it's x times 3 minus root x. This is a minus. And so, okay, to simplify this, let's not pull the 3 out. Let's make this 3 square root of x, or 3x minus x square root of x dx. And then let's rewrite that as 0 to 9 of 3x minus x to the 3 halves. And now you would do the power rule. So you would get like 2 pi times 3 halves x squared. And then it's 1 over 5 halves, which is 2/5 x to the 5 halves from 0 to 9. And now you plug in the 9 and 0. Thank you for correcting that. Does that make sense, you guys? Everybody follow it? Is everybody comfortable from there? So you plug in 9 for both x's, plug in 0 for both x's. The 0 drops out, but you plug in 9 and just simplify that. Okay. Any other questions so far? Okay, so then x equals -1 is to the left of the region. And so, yeah, it's not going to let me erase just that arrow probably, but x equals -1, let's exaggerate it and put it way over here. So x is negative, man. X equals -1 is over here. And so then we're same thing, it's the shell method. So the distance from the line to the rectangle is the right x minus left x. So x minus -1, which is x plus 1. And h of x is the height of the rectangle, which again is 3 minus the square root of x, because the top y within the rectangle minus the bottom y within the rectangle. That gets us 2 pi integral 0 to 9 of x plus 1 times 3 minus the square root of x dx. And now you have to expand that, treating this as x to the 1/2. So you like distribute or FOIL, whatever you want to call that. And then it's a bunch of power functions. All right. Any questions on those 4 problems?
Is a question like this something that would be on the written half?
To be honest, I'm still not sure. So there will
Okay.
probably be some sort of volume on the online part. Probably not one where you just type the answer for 4 different ones. Maybe one where you just type the answer for that one, or one like the ones where you're setting it up. there's a couple before this, like on the WebAssign, on the bonus, like numbers 3 and 4 would be likely to be on the final.
Okay.
Where you're doing
And
this. Does that
and
make
I
sense?
take it yeah, that makes sense. I take it the online portion is going to be the same as the previous ones where we submit our work separately at the
Yes.
end.
Yes.
All right, sounds good.
Yeah, no problem. Other questions, you guys?
Do we need to know how to do it with different cross sections?
It might. I don't want to say no for sure, but that was not like a major focus. Does that make sense?
Yeah. Yeah.
Okay, so that's not the first thing I'd be studying. Study major topics first. Once you're comfortable with everything else, then go back and look at that. There are always a few problems from the more minor topics, but not all of them. So like, average value is a more minor topic. Arc length was a little bit smaller of a topic. That is a little bit smaller of a topic. So it's, that can be there, but that's not the focus. Does that help some?
Yeah. Thank you.
Yeah. Other questions, you guys? All right, let's do this with y. I'm going to redraw all this. Let's do it with dy because I think that'll help kind of review that. Give me a second to get this written down again. So number 5 was bounded by y equals square root of x, y equals 3, and x equals 0. My bad. X equals 0. And we'll spread these out a little bit more this time. A is the x-axis. B is y equals 3. C is the y-axis. And D is x equals -1. And okay, we already had the drawing from before and figured out, okay, here's square root. And you know what, let's exaggerate that a little bit so it's easier to see what's going on, make it steeper than it really is. And then draw the horizontal line at 3 and say, okay, that's 9, 3. And so this is 3. And now, okay, we're going to do this using a dy rectangle. So we're going to go left to right. So then the base now is dy. When you do that, now you want everything solved for in terms of x. So this is obviously still y equals 3 up at the top, but instead of y equals square root of x, we're going to solve this and get x equals y squared here, which might actually be easier to deal with than square root within the integrals. And so x equals y squared is how we're going to treat that. And this is obviously still x equals 0. So now when we're doing the x-axis is now parallel to the rectangle. And so we're going to use the shell method. And so we have an r and an h, but they're functions of y rather than functions of x. And so r of y is the distance from this rectangle to the x-axis. Well, that's a vertical distance. So you take the top y minus the bottom y. But since we're using dy, you just say, okay, well, this y is y. So we get y minus 0, or just y, for the radius function. Does that make sense to everybody? Any questions on that? Okay, and then the height, when we talk about a rectangle going sideways, the base is dy, and so the height is actually left to right. And so we take the x value on the right minus the x value on the left, but we have to describe them in terms of y. So it's the right x, which is y squared, minus the left x, which is 0. And so the height function is y squared. And so the volume is 2 pi integral r times h, so y times y squared, times the thickness dy. And now we want to add all the y's in the region. Well, the lowest y in the region 0, but the biggest y in the region 3. So we go from 0 to 3. And now to just set it up, that's good enough. But to evaluate this, you would then say, okay, 2 pi integral 0 to 3 of y cubed dy, and then that's 1/4 y to the 4th, and you would go from there. Does that make sense to everybody?
Where did you get y squared?
Because you have to solve this equation for x. So we're solving that for x by squaring both sides. And we know to do that when it's dy, because you need all of the functions to be functions of y. And so what we said at the time is whenever it's dy, you want to solve everything for x. And whenever it's dx, you want to solve everything for y. Does that make sense?
Yeah.
Okay. Other questions, you guys? Okay. So then y equals 3 again is shell method, because y equals 3 is up here, so it's parallel. The r of y this time is the distance from the line to the rectangle. Well, that's top y here minus bottom y here. So we're going like the distance from here to here. Well, the top y is then 3. The bottom y is just y. So r of y is 3 minus y. H of y is the same thing. It's the right x minus the left x. So it's y squared minus 0, which is just y squared. Volume is then 2 pi RH. So 2 pi integral 0 to 3 of 3 minus y times y squared dy. And now to evaluate that, you would want to distribute the y squared. But other than that, it's not too bad. Does that make sense? Okay. Now the y-axis, the question is, or it's now a dishwasher method because it's perpendicular. So we're gonna get a large R and a small r. We got big R of y and small r of y. So big R of y is the distance from the farther end of the rectangle to the y-axis. That's the right x minus the left x. Well, the right x is y squared. The left x is 0, so it's y squared. And then small r is the distance from the closer end to the line. And the closer end is on the line. So it's 0 minus 0, which is just 0. And so volume is 2 pi integral 0 to 3 of y squared squared, and technically minus 0 squared dy, but then that simplifies to 2 pi integral 0 to 3 of y to the 4th. Oops. Make that a little bit neater. Y to the 4th dy. And yeah, somebody's asking to go over 19 after this. We'll do that next. Is everybody good to hear on this one?
Isn't this one just pi?
Oh yeah, my fault. Man, I'm glad we're reviewing. I'm rusty too. So yes, it's pi big R squared minus little r squared on this. I don't think I did that on the first problem. Let's double check. Yeah. So we were right up there. My fault. Thank you. Other questions so far?
Just a little hazy on the whole exponent thing. So an exponent to an exponent, you multiply them.
You do.
And then an exponent plus the same base, another exponent is you add them, or times you add them.
Correct. So like just real quick on the exponent stuff. So like if I have x to the 3rd times x to the 4th, that's x to the 7th. And x to the 3rd to the 4th is x to the 12th.
Okay, cool.
Does that make
Thank
sense?
you.
Okay, yeah, no problem. Other questions, you guys?
Why on this one are we doing the right x minus the left x when before we did left x minus right?
We did not do left x minus right. And where are you seeing that?
I must have wrote it differently.
You're okay. You always go right minus left if you're going sideways. And just like if you're going up and down, you always go top minus bottom. Does that make sense?
Yeah.
Okay. I
Is
think
top minus bottom also true if the equation is negative, like below the x-axis?
Yes, it is. So it's always
Okay.
top minus bottom. Now, like what the top is and what the bottom is, that is what you need to determine. Like sometimes it's the two curves, sometimes it's not. Sometimes it's like one of the curves and the line. You know what I mean? So like,
Okay.
so it depends on what the top and bottom are and what the right and left are. They could
Yeah.
be the line, but it is always top minus bottom or right minus left.
So if you had this same equation, but it was below the x-axis and you're revolving it around the x-axis, wouldn't it still
The
be?
top then would be the x-axis. It would be like
Really?
0
Okay.
minus something.
Okay.
Does that make sense?
Yeah, I had that backwards then.
That's okay. And see, sometimes it wouldn't matter because like you end up squaring it on certain ones of these. So like on this one, If you did 0 minus, it might be the same thing because you square it. So maybe you would end up with the right answer anyway. But it should always be set up as top minus bottom or right minus left.
Okay, thank you.
And sometimes it fixes itself, but sometimes it doesn't. In the shell method, it would not fix itself. You get a negative where you shouldn't have one.
Okay.
All right. Other questions, you guys? Okay. Now, I know this review is like a lot, but like doing this, I think will help you guys for next week. Like, especially on volume. I think this is something that everybody was really good at the time. But man, you probably haven't done a lot of volume for fun since September. So like, it's good to be practicing this. I know I have not looked at volume since September. I hope you have not either, but this is why I want you guys doing this. I think it helps. So, all right. So x equals -1 is over here. We'll exaggerate again. It's not quite this far probably given that scale, but all right. So again, it's dishwasher because it's perpendicular. So big R is the right X minus the left X, but now the right X is this. The left X is this. So we take the right X as y squared, and then the left X is -1. So we get y squared plus 1. And then small r is the distance from the closer end of the rectangle to the line. Well, the closer end of the rectangle is here. And so then it's the right X is now 0. The left X is -1. So it's 0 minus -1, which is then 1. So volume is pi times the integral from 0 to 3, big R squared, so y squared plus 1 squared minus little r squared, dy. And then just to get you started on this, you now square that binomial. And so you get y to the 4th plus 2y squared plus 1 minus 1. And then those, I guess we don't need the brackets and the parentheses. And then the 1 and the -1 obviously cancel, and you have some power rule stuff to do. Does that make sense, everybody? Okay, while we're on it, any quick questions about volume? And then we're going to go to number 19 next. Is everybody good? Okay, so let me pull up number 19. I have no idea what that problem is. Somehow I lost. Well, it's not. Here it is. All right. So number 19 is an integral. Okay, cool. So let's look at 19. So the one I'm getting is cosine of theta sine to the 6th theta d theta. Is that the same or similar enough, Dominic, to what you've got? Okay, cool. So this is an integral that involves powers of sine and cosine, obviously, just from looking at it. And the idea then is that you'd like to use U-substitution. And for sine and cosine, there's a quick rule that works that if one of the powers is odd, you want to let u equal the other one. So here, cosine is to the 1st and sine is to the 6th. So the easiest thing to do is to let u equal sine theta. And then if you remember back to what we were talking about at the time, it's been a long time since we've done this. Okay, so the idea is if one of them's odd, let u equal the other one. If they're both even, use half angle. And then Keegan and chat's asking, okay, what if sine is to the 5th? Then you can pick. You can either use u equals sine or u equals cosine. If cosine's to the 1st, it's easier when du is that because there's a lot less work to do, but you could technically do it either way. Does that make sense? So if they're both odd, it can be either one in general. Okay, so here though, what we're going to do is u equals sine. So then du is cosine theta d theta. And so on this one, you just move the cosine theta to the end. And you've got sine theta, or sine to the 6th theta, or sine theta to the 6th, however you want to read that. And so you don't have to rewrite anything, but normally you'd have some cosines left over that you'd then use the Pythagorean identity to rewrite in terms of sine. So this, though, is now u to the 6th du, which is then 1/7 u to the 7th plus c. And then that's 1/7 sine to the 7th theta plus c. And that'd be the answer. And so the question in chat is, okay, if sine was to the 5th, I would do it the same way. And you'd have u to the 5 here, and it would work. But you could set it up where u is cosine in that case, where you can't do that here, or at least not very easily here. Does that make sense? Any questions on this problem? All right, what else, you guys? And you can, again, it can be problems from this review, or it can be, you can name a topic that we can talk about.
Can you do one where they're both even?
Sure. So let's do it. Let's do cosine squared x sine squared x dx. So, okay, so if they're both even, then you want to use half angle formulas. Now, these rules I'm talking about are for sine and cosine, not for secant and tangent. There are different things to think about with secant and tangent. But when we have sine and cosine, we have the half angle formulas that sine squared theta is 1/2 times 1 minus cosine of 2 theta. And cosine squared theta is 1/2 times 1 plus cosine of 2 theta. And so you replace the even power with this identity, and that doesn't do the integral, it just gives you something else to work with. So here, when we have cosine times sine, we've got 1/2 times 1 plus cosine 2 theta for the cosine squared. Let's make that a little bit neater. So 2 theta. And then times sine squared is 1/2 times 1 minus cosine 2 theta d theta. And now we're going to simplify that. So I'm going to pull the 2 1/2s out. So 1/2 times 1/2 is 1/4. And then we've got 1 plus cosine 2 theta, 1 minus cosine 2 theta. And so we're going to expand that. So then, all right, we've got 1/4 integral, and this ends up being 1 minus cosine squared of 2 theta d theta, because if you distribute, you get 1 times 1 is 1, obviously, and then 1 times negative cosine 2 theta is negative cosine 2 theta, and then cosine 2 theta times 1 is positive, so those cancel, and then you get minus cosine squared. And now you split this into 2 integrals. And now this is an even power of cosine again. So we use this half angle formula again. So the first part is 1/4 theta. But now we're going to replace cosine squared of 2 theta with 1/2, which I'll pull out, and then 1 plus cosine of 4 theta. So it's like if 2 theta is here, then this is 4 theta. This is double whatever's there. So we get 1 plus cosine of 4 theta here. Now we split that up, and they both have 1/8 on them. And so now we've got 1/4 theta minus 1/8 theta. And then this is a quick U substitution where U is 4 theta. So du is 4, which means we need a 1/4 outside. So we get 1 over, whoops, 1/4 theta. We get 1 over 32 sine of 4 theta plus c, and then 1/4 minus 1/8 is 1/8. So we get 1/8 theta minus 1 over 32 sine of 4 theta plus c, and that will be the answer here. And the next question is to work problem 13, which I will do next. But any questions on this? This wasn't directly off the review, although there may be one like this, I don't know. But the question was just to do one with even powers of sine and cosine. And so that is an example of that. Any questions on it? That's good. All right. All right, so let's look at 13. Okay, so 13. And again, you may have slightly different numbers. So see if this is close enough to what you have. But I have the square root of x to the 7th and then sine of 8 plus, whoops, x to the 9/2. And then Nick in chat, is that close enough to what you've got for that problem? Okay. All right. So it's a weird looking problem. And so there aren't very many methods that would apply to this. I think it would either be U-sub or maybe parts, but parts would be real weird because of what's inside of sine. So you would start with U-sub, where we would try to let U equal the inside of sine, and that ends up working. So if I let U equal 8 plus x to the 9/2, du is 9/2 x to the 7/2. But the square root of x to the 7th is x to the 7/2. So I can rewrite this as sine of 8 plus x to the 9/2 times x to the 7/2 dx. And then I needed 9/2 inside. So I multiply here by 9/2 and multiply outside by 2/9. And so that gets us 2/9 integral sine u du. And then from there, I'll finish it for sure, but does everybody, the hard part is to get to here. Does everybody follow it to there? That's good. Any questions so far? All right, so the antiderivative of sine is negative cosine, so we get negative 2/9 cosine u plus c. That's then negative 2/9 cosine of 8 plus x to the 9/2 plus c, and that's the answer. How did I get 7/2? Because when you do the power rule in this column, you bring the 9/2 down and then you subtract 1. So 9/2 minus 2/2 is 7/2. And then this 7/2 came from the fact that I moved this to the end. So the radical thing is that if I have like the 4th root of x to the 5th power, that's x to the 5/4. So it's this number over this number. And so then the square root of x to the 7th is x to the 7/2, because this, when there's nothing here, it's a square root, so it's understood to be a 2. Does that, I'm not sure which 7/2 you mean, but does that make sense? Here it's because you subtract 1, and here it's because of a radical rule that you probably haven't used in a while, so no problem if we forget that. Do we understand what I'm saying? All right, cool. Everybody understand that? All right. Other questions, you guys? This was number 13, or similar to number 13. It does change numbers and stuff, but it's similar to 13 on your bonus. Yeah, secant tangent integral. Anyone know if there's one on the bonus? I wrote it, but I think I had secant tangent on there. I'll do the one on there if you guys want. Yeah, so number 30 is like that, and number 32.
18's like that too.
18. Okay, then we'll go back to 18 first.
I don't. It might be. I'm not sure. Look, the secant tangent both in it. 18
does have secant tangent in it, Nick. Let me do these other ones first. I will come back and do 18 though. I think what he means, I think, is like the sine and cosine ones, but secant and tangent. So like 32 and 32, 33 are like that, and there's another one somewhere. 30 is like that. So we'll do those, but we'll go back to number 18 next. That's completely fine. So let's start with number 30. So number 30 is the integral of 6 secant to the 6th of t dt. Okay, so it's a little weird that we think of this as secant and tangent, but you probably should. So when you have secant and tangent in an integral, think of it as powers of both of those, because a lot of times that approach will work. So if you have a secant in sixth, tangent is to the 0, you want to think through two possible options for this. You want to think, okay, we could let u equal secant of t, but you also want to think of the possibility of u equals tangent t. And so if we let u equal secant, du is secant tangent. And if we let u equal tangent, du is secant squared. And there should be a dt on the other one too. And the idea is you have to separate out du for these. And then the one that is not u needs to have an even power after you separate out the du, because that's what's easy to rewrite. So like here, I'm not going to be able to separate out the du because I have 6 secants, that's fine, but I don't have a tangent at all. So this approach is not going to work, or if it is, it's going to be very, very difficult. And so this isn't going to work well. There's no tangent there. But this will, at least at first, because I can separate out 2 of the 6 secants and get this to work. And what happens is once I've separated out 2 of the 6 secants, I'm left with 4 secants. And because this is an even power, it's then an easy expression to rewrite in terms of tangent. And so this is the approach we want to take on this problem. You save this for the du, so this will be replaced with du, but secant to the 4th, we rewrite using the identity. And the identity for secant and tangent, Pythagorean identity for secant tangent, says that 1 plus tangent squared x, you can do t, I guess, but 1 plus tangent squared x equals secant squared x. So because it's to the 4th, we can rewrite it as 1 plus tangent squared squared. Does that make sense to everybody? All right, and so now u is tangent, so we're going to rewrite this as 6th integral 1 plus u squared squared du. And now we expand this, so we get 1 plus 2u squared plus u to the 4th du. And now we'll split this into 3 integrals. So we get 6 integral 1 du plus 12, because we can pull the 2 out, integral u squared du plus 6 integral u to the 5th, or I'm sorry, u to the 4th du. And now we do each of these. So the integral 1 du is 6u, or it's u, but 6 is in front of there. And then we get 12 times 1/3 u to the 3rd. And then 6 times 1/5 u to the 5th plus c. And so then u was tangent, so we get 6 tangent t plus 4 tangent to the 3rd t plus 6/5 tangent to the 5th t plus c, and that's the answer. Does that make sense? Free to follow that? All right, and then on, go ahead, Nick. My bad.
On that like little third line up in the middle piece, where'd
Yep.
that 12 come from?
Because I pulled the 2 out.
Oh,
And
okay.
the
that's-
6 is on
that's
there.
what
You're
saying.
good. You're good. Does that make sense? All right. Other
Yeah.
questions, guys? Okay, so if when you get to these on the review, 32 and 33 are going to be real similar to that. 33, if we look at them real quick, here's what I've got. If you have on 32, I would u sub out the 2x first. So I would like let u equal 2x, and then du is 2. So you get a 2 here and a 1/2 outside, and you'll get tangent to the 3rd u, secant to the 5th u, with 3 halves instead of 3, and then follow the same idea. I think on this one you would let u equal secant, but mess with it and see. And then cosecant, cotangent have almost exactly the same relationships that secant and tangent have. So 1 plus cotangent squared is cosecant squared, and the derivative of cosecant is negative cosecant cotangent, and the derivative of cotangent is negative cosecant squared. And so it's almost identical to the secant tangent. Let's try those, and then we can go over more of them tomorrow if we need to. I'm happy to do that, but that would be good to try these, having seen what we just did on number 30, or whatever that was. Number 30. Okay, so we can do a trig sub. Let me do number 18, just because somebody did bring that one up, and it is related to secant and tangent. It's not exactly what he meant, and we'll do trig sub right after this one. So number 18, is this one. This is what it was either Nick or Dominic. Is this the one you were talking about? It is, right? I think maybe it wasn't you guys. Somebody said 18, so let's do that one. It's worth doing. So let's look at that. So again, your numbers may be a little different from mine, but man, it just disappeared. All right, so we got the integral of e to the tangent 7x, and this is just a weird u sub that I think is worth looking at. Secant squared of 7x, and so because of the e there, again, it's a very weird setup. So the most direct thing we could do is let u equal the power of e here, where we would try to do e to the u du, and that works real well. You just have to be careful of the chain rule, which is why I wanted to go through this problem. So the derivative of tangent of 7x is secant squared 7x, but then times 7 because of the chain rule. And we can rewrite that as 7 secant squared of 7x dx. So then it's already set up in the form you want. And so we're going to multiply inside by 7. And then in order to do that, we're going to multiply outside by 1 over 7. So we get 1/7 e to the u du inside the integral, and then 1/7 e to the u plus c. And that's 1/7. Then I don't think you were even asking how to do this problem, but I thought it was worth looking at. It looks like it's going to be a secant tangent one. It's not because that e, but that is it on that one. Any questions on that problem? This was number 18. You probably have a different, maybe not 7, but same idea. Okay, and then a trig sub. Let me find one. Does anyone know what number on the review or on the bonus is a trig sub? I can do one off the review, or I can make one up, or I can find one from an old worksheet. Let me scroll through real quick and see. Okay, 34, 35 are trig sub. Yeah, 36 could be trig sub. Let's do 35. I think 34 is easier. Let's do 35 because I think 34 is easier. You guys try it, and we can work it tomorrow again if we want to. So 35, the one I've got is the integral of 1 minus 9x squared dx. Again, your numbers might be different. Maybe you have 16x squared or 25x squared or something, but same idea. So trig sub, and you know what, real quick, let me show you guys. So these 3 problems are good to look at together. So 34, 35, 36, they all involve square roots that you could get rid of using trig sub. And 34 and 35 should be done using trig sub, but 36 should not be done using trig sub. Why not? What could you do on 36 instead?
Couldn't you do u sub?
You could do u sub. So if you do u equals 4 minus t squared, du is negative 2t, which is sitting right here. I mean, you have to deal with that coefficient, but it's easy to deal with. And so you can use trig sub here, but it's easier not to. On 35 and 34, I think the easiest way is to use trig sub. So let's go back and do 35. And so what you do once we determine that we want to use trig sub is we pick x. Man, why is it not sharing? There it goes. All right. So we pick x, and we pick for x a coefficient and a trig function. So the coefficient you use to try to make these coefficients match each other. And so you want to cancel the 9 and end up with 1. So the way you do that is you put a 3 in the bottom and you put a 1 in the top. Remember that the one you're able to change is the one that is with x. So the coefficient of x, you're able to change that by plugging in. You're not able to change the other one. So we want 1/3 here. And then the idea back when we were talking about this is that if it's 1 minus a trig function squared, we want to use sine because of that identity. If it's plus in either order, we want to use tangent because of this property. And then if it's subtraction, but in the other order, so if it's trig function squared minus 1, we want to use secant because that'll get us positive tangent squared. So subtraction, if it's a number minus the trig function, you use sine. If it's a trig function minus 1, you use secant. If it's addition, the order does not matter and you use tangent. So here we're going to use sine. So we let x equal 1/3 sine of theta. And then we figure out what dx is. Dx is the derivative of that, which is 1/3 cosine theta, but then times d theta. So dx is the derivative times d theta. And then what we always did was we tried to get rid of the square root, but we did it on the side. So 1 minus 9x squared under the square root can be replaced with square root of 1 minus 9 times 1/3 sine theta squared. That's 1 minus 9 times 1/9 sine squared theta. The 9s cancel. We get 1 minus sine squared, which is cosine squared. Square root of that is cosine of theta. And I'm going quick because I want to get this in, but does everybody follow that? Pretty good. Okay. So now the square root gets replaced with this answer down here. On this problem, we don't have any x's that aren't in a square root. But if we did, you would replace the x's outside the square root with 1/3 sine theta. And then you need to remember to replace dx with whatever we found for dx. So dx is 1/3 cosine theta d theta. So this stuff is on the side and that's on the side, but this is the first step in the main problem once we do all this. Now we simplify this and do this integral. So we pull the 1/3 out. Cosine times cosine is cosine squared. And the way we do this integral is we happen to use half angle formulas. So the one we said earlier is that cosine squared theta is 1/2 times 1 plus cosine of 2 theta. So we replace this with 1/3 times 1/2. Integral 1 plus cosine of 2 theta d theta. That's 1/6, and we distribute it. So we get 1/6 integral of 1 d theta plus 1/6 integral cosine 2 theta d theta. Everybody good to hear? Sorry, I know I'm going quick. That's good. Okay, so the integral of 1 d theta is theta. The integral of cosine 2 theta is 1/2 sine 2 theta because of a quick U-substitution. Now we're going to go back to x, and we do that using a triangle. So we go to the original substitution. So x is 1/3 sine theta, and we solve for the trig function. So sine theta is 3x, or we can think of it as 3x over 1. It's good to think of it as a ratio like that. So that's easier to draw the triangle. And so now we draw a triangle in the first quadrant. And this angle is theta. Sine is 3x over 1, so opposite over hypotenuse, or y over r, is 3x over 1. So the easiest way for that to happen is label the y side as 3 and the r side as 1. The Pythagorean theorem gets us that this side is the square root of 1 minus 9x squared. And now we're going to go back to this answer and try to use the triangle to go back to theta, to go back from theta to x. So, all right, so we take a second and use the double angle formula for sine. And it says that sine of 2 theta is 2 sine theta cosine theta. And so now, okay, the 1/2 and the 2 cancel. So now, theta not in a trig function, we use inverse trig. So we use the inverse trig function from this equation. So sine theta is 3x over 1. So then theta is the inverse sine of 3x within the domain restriction, which this is. And then we have the 1/6, and sine theta we read right off the triangle. Sine theta is opposite over hypotenuse, or y over r, so it's 3x over 1. Cosine is adjacent over hypotenuse, or x over r, so it's the square root of 1 minus 9x squared over 1. We can simplify this just a little bit. And so we get 1/6 inverse sine of 3x plus x square root of 1 minus 9x squared over 2 plus c, because the 3 cancels with the 6. But that is the answer on that problem. Does that make sense? That is a lot. And we've not done that in a long time. Does everybody follow what's going on? Questions? Okay. All right, guys, I think we're going to end it here for today. If you have like quick questions, let me know, and you can stick around. If not, we will pick up again tomorrow at 12:30. I think this works pretty well where you guys ask questions from the review. If you have other stuff you'd like to see, definitely let me know that, and we'll try to do that. We'll do this today and tomorrow for sure, and then we'll talk tomorrow about the review time on Sunday. And then if we want to do a review on Friday, I'm open to that as well. I'm not able to do Saturday, but I can do Friday and if we need to, and then definitely on Sunday. Any quick questions before we sign off here? Is everybody good?
For the one we just did, where did the inverse sine come from again?
No, you're good, Gabby. So when you have theta not in a trig function, you go to this equation where you've solved for the trig function, and it's inverse that of this other side. Does that make sense? So theta is inverse sine of 3x. If this was secant, theta would be inverse secant of 3x.
Okay.
That makes sense. And you only want to use that when theta is not inside of a trig function.
Okay.
Okay. All right. Other questions, you guys? Okay. Well, then that's it for today. Thanks for coming, you guys, and I hope I'll see you tomorrow. Good luck with everything this week. I know we've got a lot going on. So good luck. See you guys.